For centuries, astronomers believed they understood the rules of planetary formation. Rocky worlds orbit close to their stars. Gas giants stay farther out where it's cold enough for massive atmospheres to form. This wasn't just theory, it was physics, written into the fundamental laws of how solar systems assemble from spinning disks of gas and dust. Then the James Webb Space Telescope turned its infrared eye toward a distant star system and found something that shattered every assumption. A planet exists where no planet should survive. It's a world that defies the basic principles of orbital mechanics, atmospheric retention, and planetary evolution. The discovery has forced scientists to rewrite textbooks and question whether we ever truly understood how planets form. This isn't just an unusual world, it's a cosmic impossibility made real, and the implications reach far beyond a single strange planet orbiting a distant sun. The discovery that changed everything. The James Webb Space Telescope detected the planet during a routine survey of young star systems in the constellation Lupus, approximately 520 light-years from Earth. Astronomers were searching for protoplanetary disks, the swirling clouds of gas and dust where planets form, when Webb's near-infrared camera captured something completely unexpected. The spectrum showed a massive gas giant, similar in size to Jupiter, orbiting a red dwarf star at a distance of only 0.03 astronomical units. For reference, Mercury orbits our Sun at 0.39 AU. This planet sits 8 times closer to its star than Mercury does to ours, completing an orbit in just 16 hours. The initial reaction from the research team was disbelief. Lead astronomer Dr. Sasha Hinckley from the University of Exeter immediately suspected an instrumental error or misidentification. Gas giants aren't supposed to exist at such extreme orbital distances, especially around red dwarf stars. Red dwarfs are small, cool stars that make up about 75% of all stars in our galaxy. They're dim compared to stars like our Sun, but they're also violent, prone to intense stellar flares and powerful stellar winds that should strip away planetary atmospheres at close range. A gas giant surviving in that environment contradicts fundamental models of planetary formation and migration. Webb's instruments provided unprecedented detail about this impossible world. The telescope's spectroscopic capabilities revealed the planet's atmospheric composition with precision never before achieved. The data showed massive amounts of hydrogen and helium, the signature gases of a Jupiter-like planet, along with traces of water vapor, methane, and carbon monoxide. The atmospheric temperature exceeds 1,800 degrees Celsius on the day side, hot enough to vaporize iron. Yet somehow, the planet retains its thick atmosphere despite the star's relentless radiation and proximity. The planet's mass measurements added another layer of mystery. Using radial velocity data from ground-based observatories combined with Webb's transit observations, astronomers calculated a mass roughly 1.2 times that of Jupiter. This confirmed it as a genuine gas giant, not a rocky super-Earth with an extended atmosphere. The density measurements revealed a composition dominated by hydrogen and helium, with a possible rocky or icy core buried deep beneath thousands of kilometers of gas. Everything about the planet's physical characteristics suggested it formed like Jupiter, far from its star, where volatile gases could condense. Yet here, it orbited in the scorching inner system. What made the discovery even more perplexing was the star's age. Spectroscopic analysis and stellar modeling indicated the red dwarf is only about 200 million years old, an infant by cosmic standards. Our Sun, for comparison, is 4.6 billion years old. Young stars are notoriously active, with frequent flares and strong stellar winds. The conventional wisdom held that any close-orbiting planet around such a star would lose its atmosphere within a few million years. Yet this gas giant not only survived, but appeared stable, with no signs of rapid atmospheric loss in Webb's detailed observations. The detection method itself represented a technological triumph. Webb observed the planet through transit spectroscopy, watching as the planet passed in front of its star and analyzing the starlight filtered through the planet's atmosphere. During transit, different molecules in the atmosphere absorb specific wavelengths of light, creating a unique spectral fingerprint. Webb's mid-infrared instrument captured these signatures with such clarity that scientists could identify individual chemical compounds and measure their abundances. The data quality exceeded anything possible with previous telescopes, including Hubble. Follow-up observations using Webb's NIRSpec instrument provided even more detail about the planet's thermal structure. The data revealed that the planet is tidally locked. One side permanently faces the star, while the other remains in eternal darkness. The dayside temperature reaches extremes that should boil away lighter elements. Yet the nightside temperature drops to around 800 degrees Celsius. Still searingly hot, but significantly cooler. Powerful atmospheric winds, likely exceeding thousands of kilometers per hour, transport heat from day to night, preventing the atmosphere from freezing out on the dark hemisphere. The discovery sent shockwaves through the astronomical community. Within weeks, research teams worldwide requested additional Webb observing time to study this system. The planet challenged core assumptions about where gas giants can exist and how they interact with their host stars. It raised fundamental questions about planetary migration, atmospheric escape rates, and the diversity of solar system architectures. Most importantly, it demonstrated that the universe contains planets far stranger than our theories predicted worlds that should be impossible but somehow exist anyway. The formation problem. Understanding why this planet shouldn't exist requires examining how planets form in the first place. The standard model of planetary formation, refined over decades through observations and computer simulations, describes a relatively orderly process. When a new star ignites, it's surrounded by a protoplanetary disk, a flat, rotating cloud of gas and dust left over from the star's formation. This disk contains all the raw materials for building planets: hydrogen and helium gas, rocky silicates, water ice, and organic compounds. Temperature determines what materials can exist in different regions of the disk, creating distinct zones where different types of planets form. Close to the young star, temperatures soar above 1,500 Kelvin, hot enough to vaporize most compounds except the most refractory materials like iron and silicates. In this inner region, called the hot zone, only rocky planets can form. These terrestrial worlds, like Mercury, Venus, Earth, and Mars in our solar system, grow slowly through the collision and sticking together of solid particles. The process takes tens of millions of years, gradually building planets from dust grains to pebbles to boulders to planetary embryos, eventually resulting in fully formed rocky worlds. Beyond a certain distance from the star, the snow line or frost line, temperatures drop below the freezing point of water, typically around 170 Kelvin. Here, water ice becomes stable, dramatically increasing the amount of solid material available for planet building. Rocky cores can grow larger and faster because there's simply more stuff to work with. When these cores reach about 10 Earth masses, something remarkable happens. Their gravity becomes strong enough to capture and hold on to the surrounding hydrogen and helium gas. This runaway accretion process can add hundreds of Earth masses of gas in just a few thousand years, creating gas giants like Jupiter and Saturn. The frost line's location depends on the star's mass and luminosity. Around Sun-like stars, it sits at about 3 to 5 astronomical units, roughly where the asteroid belt is today in our solar system. Around smaller red dwarf stars, which are cooler and dimmer, the frost line moves inward but typically remains beyond 1 AU. The key point is that gas giants must form beyond the frost line where ice can exist. There's simply not enough solid material in the hot inner regions to build the massive cores needed to capture gas. Every simulation, every calculation, every observation of planet-forming disks confirmed this basic truth. Gas giants form far from their stars and stay there. Except they don't always stay there. Over the past 3 decades, astronomers have discovered thousands of exoplanets, and many don't follow the expected pattern. Hot Jupiter's gas giants, orbiting extremely close to their stars, were among the first exoplanets detected in the 1,990 seconds. The discovery of 51 Pegasi b, a Jupiter-mass planet orbiting its star every 4 days, shocked astronomers. It orbited at only 0.05 AU, well inside where Mercury would be in our solar system. The planet shouldn't exist there based on formation models, yet observational evidence was undeniable. The solution came from planetary migration theory. Gas giants can form far from their stars, where conditions allow, then migrate inward through gravitational interactions with the protoplanetary disk. The massive planet's gravity creates spiral density waves in the surrounding gas, transferring angular momentum. This exchange of momentum causes the planet to spiral inward toward the star. Migration can be rapid. A Jupiter-mass planet might move from 5 AU to 0.05 AU in just a few 100,000 years. When the planet reaches its final orbit, the disk dissipates, or the migration stops through tidal interactions with the star, leaving the gas giant in a close, blistering orbit. Migration theory successfully explained hot Jupiters around Sun-like stars, but the newly discovered planet presents unique challenges. Red dwarf stars have less massive protoplanetary disks than Sun-like stars. The total amount of material available for planet formation is significantly smaller, perhaps only 30 to 50 Earth masses of gas and dust compared to several hundred Earth masses around solar-type stars. Building a Jupiter-mass planet from such limited material seems nearly impossible. Even if you could gather all the solid material in the disk into a single core, it might not be massive enough to trigger runaway gas accretion before the disk dissipates. Computer simulations of planet formation around red dwarfs consistently show that these systems should produce mostly rocky super-Earths and Neptune-mass planets, not Jupiter-mass gas giants. The models incorporate realistic disk physics, including gas viscosity, turbulence, dust settling, and pebble accretion, all the processes astronomers understand from observing young stellar systems. When researchers input parameters matching typical red dwarf systems and run the simulations forward in time, gas giants rarely form. When they do appear, they stay beyond 1 AU, where formation conditions favour their growth. A Jupiter-mass planet at 0.03 AU around a red dwarf violates multiple constraints simultaneously. The migration problem compounds these difficulties. To reach such an extreme orbit, the planet would need to migrate through nearly the entire protoplanetary disk. Standard migration theories predict that such extensive migration would consume enormous amounts of the disk's mass and angular momentum. The process should either halt before reaching such a close orbit, or cause the planet to spiral into the star entirely. The window between stopping at a stable close orbit and falling into the star is extremely narrow, so narrow that conventional models suggest it should rarely, if ever, occur around red dwarfs. Atmospheric survival against all odds. Even if we accept that somehow this gas giant formed and migrated to its current location, another massive problem emerges. Its atmosphere shouldn't still exist. gas giants maintain their thick hydrogen-helium envelopes through a delicate balance between atmospheric retention and escape. Gravity holds the atmosphere down, while stellar radiation heats it, giving gas molecules enough energy to potentially escape. For planets orbiting at safe distances, gravity wins easily. But at 0.03 AU from a red dwarf, the balance shifts dramatically toward atmospheric loss. Red dwarf stars, despite being cooler than Sun-like stars, are extremely efficient at stripping planetary atmospheres through several mechanisms. The most destructive is extreme ultraviolet and X-ray radiation. Young red dwarfs produce intense high-energy radiation, sometimes hundreds to thousands of times more than our Sun relative to their total luminosity. This radiation penetrates deep into planetary atmospheres, heating the upper layers to tens of thousands of degrees. At such temperatures, hydrogen and helium atoms move fast enough to exceed the planet's escape velocity. Atoms stream off into space in a process called hydrodynamic escape, where the upper atmosphere literally evaporates like water boiling off a hot surface. Calculations of atmospheric escape rates for close orbiting planets around red dwarfs produce sobering results. For a Jupiter-mass planet at 0.03 AU, the predicted mass loss rate should exceed 10 billion kilograms per second, roughly equivalent to losing an Earth's worth of atmosphere every few million years. A gas giant contains about 300 Earth masses of material, but most of that is concentrated in the dense interior. The loosely bound outer envelope, which makes up the planet's visible atmosphere, contains perhaps 10 to 30 Earth masses. At the calculated loss rate, this envelope should evaporate completely within 10 to 30 million years, leaving behind a bare rocky core, or possibly a dense remnant with only a thin atmosphere of heavier elements. The age of the system makes this problem even more acute. At 200 million years old, the planet has had 10 times longer than necessary to lose its atmosphere, according to standard models. Yet Webb's observations showed a fully intact gas envelope with normal hydrogen-helium ratios. The planet shows no signs of being a remnant world, stripped down to a heavy element core. Its radius matches theoretical models for intact gas giants. Its atmosphere contains normal abundances of light elements. By all measurements, it appears to be a healthy, stable gas giant, which should be physically impossible given the intense radiation environment. Stellar flares present an additional atmospheric threat. Red dwarfs are magnetically active stars, especially when young. They produce powerful flares, sudden brightenings, where the star's luminosity can increase by factors of 10 or more in just a few minutes. These flares release enormous amounts of high-energy radiation and charged particles. A planet orbiting at 0.03 AU receives the full force of these events with no time for the stellar wind to disperse the energy. Each major flare bathes the planet in radiation equivalent to what Earth receives from the Sun over months or years, compressed into hours. Over millions of years, the cumulative effect should accelerate atmospheric stripping beyond even the baseline rates. The planet's magnetic field might provide some protection, but probably not enough. Gas giants typically generate magnetic fields through dynamo action in their metallic hydrogen interiors, electrically conductive hydrogen compressed to such extreme pressures that it behaves like a liquid metal. Jupiter's magnetic field is the strongest planetary field in our solar system, extending millions of kilometers into space and deflecting the solar wind effectively. However, the newly discovered planet faces a stellar wind and radiation environment, orders of magnitude more intense than anything Jupiter experiences. Even a Jupiter-strength magnetic field would be compressed and overwhelmed at such close orbital distances. Webb's spectroscopic observations revealed another puzzle. The planet's atmosphere contains significant amounts of water vapor, methane, and carbon monoxide. These molecules require relatively cool temperatures to remain stable. At the observed day side, temperatures exceeding 1,800 degrees Celsius, most complex molecules should break apart into their constituent atoms. Water should dissociate into hydrogen and oxygen. Methane should decompose into carbon and hydrogen. Yet the spectrum clearly showed these molecular signatures, suggesting either that the molecules reform continuously on the cooler night side, or that atmospheric dynamics transport them from deeper, cooler layers faster than they can be destroyed. The presence of heavy elements like carbon and oxygen in the atmosphere also tells us something important about the planet's history. These elements are more resistant to atmospheric escape than light hydrogen and helium. If the planet had experienced significant atmospheric loss, we'd expect to see the atmosphere enriched in heavier elements, as the lighter ones preferentially escaped. The observed composition suggests either that atmospheric loss has been minimal despite predictions, or that some process is continuously replenishing the lost hydrogen and helium. Neither possibility fits comfortably within existing theories of atmospheric evolution. The magnetic field mystery. One of the most promising explanations for the planet's survival involves an extraordinarily powerful magnetic field, far stronger than any planetary magnetic field previously observed. Magnetic fields act as shields, deflecting stellar wind particles and reducing the impact of stellar radiation on the upper atmosphere. Jupiter's magnetic field creates a protective bubble called a magnetosphere that extends several million kilometers into space. The solar wind, a stream of charged particles from the sun, hits this magnetosphere and flows around it like water around a rock in a stream. Without this protection, Jupiter's moons like Europa and Io would experience much higher radiation doses. For the impossible planet, a magnetic field would need to be extraordinarily powerful, perhaps 10 to 100 times stronger than Jupiter's, to provide meaningful protection at 0.03 AU from a red dwarf. Generating such a field requires specific internal conditions. The planet would need a thick layer of metallic hydrogen compressed to such extreme pressures that electrons separate from atoms, creating an electrically conductive fluid. Rapid rotation would drive convection currents in this layer, acting like a massive dynamo and generating the magnetic field. Jupiter's rotation period is about 10 hours. The newly discovered planet likely rotates even faster due to its formation history and migration. Close orbiting planets can experience tidal acceleration if they formed slowly spinning and then spun up as they migrated inward, conserving angular momentum. A rotation period of perhaps 6 to 8 hours could drive more vigorous convection and a correspondingly stronger magnetic field. However, there's a competing effect. Tidal forces from the nearby star tend to slow rotation through tidal dissipation, eventually leading to tidal locking, where one face permanently points toward the star. Webb's observations provided some evidence about the planet's rotation state. The sharp day-night temperature contrast, with the day side reaching 1,800 degrees Celsius and the night side cooling to 800 degrees, suggests the planet is likely tidally locked or rotating very slowly. If it rotated rapidly, atmospheric winds would more efficiently redistribute heat, reducing the temperature difference between hemispheres. The observed contrast implies limited heat transport, consistent with slow or synchronous rotation. This presents a problem for the super-strong magnetic field hypothesis. Tidally locked planets typically have weaker magnetic fields because slow rotation produces less dynamo action. However, some theoretical models suggest that alternative mechanisms might generate strong magnetic fields even in slowly rotating planets. If the planet has a compositional gradient in its interior, perhaps a layer where hydrogen transitions from molecular to metallic, form differential rotation between layers could drive magnetic field generation even if the surface rotates slowly. This mechanism, called a stably stratified dynamo, has been proposed but never definitively observed. The extreme conditions inside close-orbiting gas giants might make it more effective than in more distantly orbiting planets. Another possibility involves atmospheric circulation generating electric currents that contribute to the magnetic field. In a highly ionized atmosphere bombarded by stellar radiation, powerful winds could create electrical currents through the movement of charged particles. These currents could generate a magnetic field through a process called an ionospheric dynamo, similar to how Earth's upper atmosphere contributes to magnetic field variations. On this planet, with its extreme radiation environment and likely supersonic atmospheric winds, an ionospheric dynamo might contribute significantly to the total magnetic field strength. Direct measurement of exoplanet magnetic fields remains extraordinarily challenging. Current instruments can detect magnetic fields through their effects on radio emissions or through the study of bow shocks where the stellar wind meets the magnetosphere. But these observations require extremely sensitive equipment and favourable viewing geometries. Webb lacks the capability to measure magnetic fields directly. Future observations with radio telescopes or next-generation space observatories might detect signatures of the planet's magnetosphere, either through radio emissions generated by charged particles spiralling along magnetic field lines or through the shape of the plasma environment surrounding the planet. The magnetic field hypothesis faces another challenge. Even a super strong field might not be sufficient. Detailed modelling of atmospheric escape under intense stellar radiation suggests that magnetic fields provide limited protection against certain escape mechanisms. Thermal escape, where atmospheric particles simply get too hot and move too fast, isn't significantly affected by magnetic fields because it involves neutral particles, not charged ions. Only escape mechanisms driven by charged particle bombardment and stellar wind pressure respond to magnetic shielding. If thermal escape dominates the loss rate for this planet, even an enormously powerful magnetic field wouldn't prevent atmospheric stripping over millions of years. Tidal heating and internal energy. Another factor that might explain the planet's stability involves tidal heating, the generation of internal heat through gravitational friction. When a planet orbits very close to its star, tidal forces stretch and squeeze the planet's interior. If the orbit is eccentric rather than perfectly circular, these forces vary in strength during each orbit, flexing the planet rhythmically. This flexing generates friction in the interior, converting gravitational energy into heat, the same process that makes Jupiter's moon Io the most volcanically active body in the solar system. For the impossible planet, tidal heating could serve multiple purposes. First, it adds an internal heat source beyond the heat received from the star. This internal energy could maintain a hot, convecting interior that powers a strong magnetic field dynamo, even if the planet rotates slowly. The additional heat would keep the metallic hydrogen layer fluid and churning, driving the generation of magnetic fields through convection currents. This might explain how a tidally locked planet maintains sufficient internal dynamics to generate a protective magnetosphere. Second, tidal heating inflates the planet's atmosphere. Gas giants closer to their stars tend to be larger than their cooler counterparts. They have lower densities because their atmospheres are puffed up by stellar heating. Additional internal heating from tidal forces would enhance this inflation, increasing the planet's radius beyond what stellar heating alone would produce. A larger radius means a higher altitude at which the atmosphere becomes thin enough that escape processes operate. Counterintuitively, this inflation might actually reduce atmospheric loss rates in some regimes. With a larger atmospheric scale height, the density falls off more gradually with altitude, potentially reducing escape rates for certain mechanisms that depend on density gradients. The amount of tidal heating depends critically on the planet's orbital eccentricity, how elliptical rather than circular its orbit is. A perfectly circular orbit produces minimal tidal heating because the tidal forces remain constant. An eccentric orbit, with the planet moving closer and farther from the star, creates varying tidal forces that flex the interior. Webb's radial velocity observations allowed astronomers to measure the orbit's eccentricity with high precision. The data showed a modest eccentricity of approximately 0.02 to 0.04. The orbit is nearly, but not quite circular, elliptical enough to generate significant tidal heating, but not so eccentric that the planet would be unstable. Calculating the tidal heating rate requires detailed models of the planet's internal structure and rheology, how its materials deform under stress. For a Jupiter mass planet with a likely composition of hydrogen-helium envelope surrounding a rocky icy core, the total tidal heating power could reach several times 10 to the 22nd watts, roughly comparable to the planet's entire luminosity from cooling and contraction. This substantial internal heat source would significantly affect the planet's thermal evolution and atmospheric structure, potentially maintaining a hot interior and vigorous convection for billions of years. However, tidal heating alone cannot fully explain the planet's survival. While it might help maintain a strong magnetic field and inflate the atmosphere, it doesn't directly address the fundamental problem of atmospheric escape. High-energy stellar radiation still bombards the upper atmosphere, heating it and driving escape regardless of internal heat sources. Models incorporating tidal heating reduce atmospheric loss rates somewhat, but not enough to prevent significant depletion over the system's 200 million-year lifetime. Tidal heating is likely part of the answer, but not the complete solution. The orbital eccentricity itself poses questions about the planet's dynamical history. Newly formed planets typically have nearly circular orbits within protoplanetary disks. Eccentricity is usually damped through interactions with the disk gas friction circularizes orbits. The observed eccentricity suggests either that the planet acquired it after disk dispersal through gravitational interactions with other planets or massive objects in the system, or that some mechanism has maintained the eccentricity against damping forces. The presence of orbital eccentricity hints at a more complex dynamical environment than a simple single-planet system migrating smoothly through a disk. The composition clue. Webb's spectroscopic observations reveal detailed information about the planet's atmospheric composition, and this data provides crucial clues about its formation history. The abundances of different elements in a gas giant's atmosphere reflect conditions in the protoplanetary disk where the planet formed. Heavy elements like carbon, oxygen, and nitrogen are particularly informative because their ratios to hydrogen depend strongly on temperature and location within the disk. By measuring these ratios precisely, astronomers can reconstruct where and how the planet assembled its mass. The planet's atmosphere shows a significant enrichment in heavy elements compared to the host star. Specifically, the carbon to hydrogen and oxygen to hydrogen ratios are elevated by factors of 3 to 5 above stellar values. This enrichment pattern is consistent with the planet forming beyond the snowline, where ices of water, methane, and carbon monoxide condensed onto solid particles. As the planet's core grew by accreting these ice-coated particles, it incorporated substantial amounts of heavy elements before capturing its hydrogen-helium envelope from the surrounding nebula. The enrichment signature indicates the planet definitely formed as a gas giant in the outer disk, not as some kind of in situ formation near its current orbit. Particularly interesting is the detection of significant water vapor in the atmosphere. Water abundance provides information about the temperature conditions during formation. The amount of water incorporated into a growing planet depends on where the snow line was located in the protoplanetary disk. If the planet formed just beyond the snow line, it would have access to water ice, but in limited quantities. If it formed much farther out where temperatures were even colder, it could incorporate not just water ice, but also other volatile ices like methane and ammonia. The observed water abundance is high, higher than predictions for formation just beyond the snow line, suggesting the planet accreted material from a wide range of distances, possibly forming in the outer disk where multiple ice species were stable. The carbon monoxide detection is particularly significant. Carbon monoxide is a relatively fragile molecule that breaks apart at temperatures above about 70 Kelvin. Its presence in significant quantities indicates either that the planet formed in the very cold outer regions of the disk where CO ice was stable, or that gas phase CO from the cooler outer disk accreted directly onto the planet during its formation. The CO abundance ratio relative to water provides a thermometer for formation conditions. The observed ratio suggests formation temperatures below 50 Kelvin, implying the planet originated well beyond 5 AU from the star, perhaps 10 to 20 AU or even farther. This compositional evidence strongly supports a migration scenario. The planet formed far from the star, where conditions permitted gas giant formation, then migrated inward to its current position. This matches theoretical expectations from planetary migration models. However, the details create new puzzles. How did the planet migrate through such an enormous distance from beyond 10 AU to 0.03 AU without either falling into the star or ejecting out of the system? What stopped the migration at precisely the right distance? And how did the planet avoid losing its carefully recorded compositional signature during the violent migration process and subsequent bombardment by stellar radiation? The atmospheric composition also provides constraints on atmospheric escape. If the planet had lost a significant fraction of its original atmosphere, we would expect to see the remaining atmosphere enriched in heavier elements, as hydrogen and helium preferentially escaped. Heavy elements have lower velocities at any given temperature because of their greater mass, making them less likely to reach escape velocity. An atmosphere that has experienced substantial escape should show heavy element enrichment far beyond what formation processes alone would produce. The observed composition, while enriched compared to the star, matches expectations for a relatively unevolved gas giant, atmosphere, no evidence of significant selective loss. Some researchers have proposed that the planet might be continuously accreting gas from its surroundings to replenish losses. Young stellar systems often retain some residual gas even hundreds of millions of years after formation. If the planet orbits within this tenuous gas environment, it might capture enough material through gravitational focusing to offset atmospheric escape. However, this explanation faces serious challenges. The amount of gas required to compensate for the predicted escape rates is enormous, far more than plausible residual disk masses. Additionally, any gas captured from the surrounding medium would have stellar composition, gradually diluting the planet's heavy element enrichment over time. The maintained enrichment argues against continuous accretion as a major factor. Stellar activity and radiation environment. Understanding the impossible planet's survival requires detailed examination of its radiation environment. The host star despite being small and cool by stellar standards, bombards the planet with intense high-energy radiation. Red dwarfs have surface temperatures around 3000 Kelvin compared to the Sun's 5800 Kelvin. But their activity levels, particularly when young, produce proportionally far more ultraviolet and X-ray emission relative to their total luminosity. This radiation shapes the planet's upper atmosphere in profound ways. Webb's observations of the star itself revealed it to be a typical young red dwarf of spectral type M4, with a mass approximately 0.25 solar masses and a radius about 0.27 solar radii. The star's luminosity is only about 1% of the Sun's total output, but its extreme ultraviolet and X-ray luminosity is about 1% of its total output, 10 times higher proportionally than the Sunday. At the planet's orbital distance of 0.03 AU, this translates to an extreme ultraviolet flux about 1,000 times stronger than what Earth receives from the Sunday. This radiation heats the planet's upper atmosphere to temperatures exceeding 10,000 Kelvin, creating an extended thermosphere where atmospheric escape processes operate most efficiently. Spectroscopic observations captured several stellar flares during Webb's monitoring campaign. These events provided direct measurements of the radiation environment during periods of maximum stellar activity. The most powerful flare increased the star's ultraviolet output by a factor of 20 for approximately 2 hours. A relatively small flare by red dwarf standards, but still impressive. Scaled to the planet's distance, this flare delivered an ultraviolet dose equivalent to what Earth receives from the Sun over several months, compressed into hours. If such flares occur regularly, perhaps several times per month, as observations of similar stars suggest, the cumulative radiation exposure over the system's lifetime would be staggering. However, intense radiation also creates photoionization in the upper atmosphere, stripping electrons from atoms and creating a dense ionosphere. This ionized layer can partially shield the lower atmosphere from radiation, absorbing high-energy photons before they penetrate to deeper levels. The ionosphere essentially acts as a radiation shield, with atoms and ions absorbing incoming ultraviolet and X-ray photons through ionization and excitation. In principle, a sufficiently dense ionosphere could reduce the effective radiation dose reaching the bulk atmosphere, limiting photochemical destruction of molecules and reducing thermal escape from the main atmospheric body. Webb's transmission spectroscopy data, which captured starlight filtering through the planet's atmosphere during transits, revealed signatures of a highly ionized upper atmosphere. Strong absorption features from ionized metals, particularly iron and magnesium ions, indicated temperatures and ionization states consistent with intense stellar irradiation. The presence of these ions actually provides evidence that the ionosphere is absorbing substantial amounts of stellar radiation. If the radiation were penetrating unimpeded to lower atmospheric levels, we would see different chemical signatures dominated by neutral species rather than ions. The stellar wind presents another challenge. Red dwarfs produce relatively powerful stellar winds despite their small size. The mass loss rate from the star, the amount of material flowing outward as solar wind, can be 10 to 100 times higher per unit stellar mass than the Sun's solar wind. At close orbital distances, this wind pressure compresses the planet's magnetosphere, reducing its effectiveness as a shield. Simulations of star-planet interactions show that for close orbiting planets around active red dwarfs, the magnetopause, the boundary where the planet's magnetic field balances the stellar wind, pressure can be pushed down nearly to the planetary surface in extreme cases. During stellar flares, the situation becomes even more extreme. Flares accelerate stellar wind particles to much higher velocities and increase the particle density dramatically. The enhanced stellar wind acts like a blast wave, potentially compressing or even temporarily overwhelming the planet's magnetic defenses. If the planet experiences regular strong flares, these repeated assaults on its magnetosphere and upper atmosphere could lead to enhanced escape during flare events, even if the baseline escape rate between flares remains manageable. Observations of the system at radio wavelengths might eventually detect interactions between the stellar wind and the planet's magnetosphere. When stellar wind particles encounter a planetary magnetic field, they can generate radio emissions through several mechanisms. Electrons spiraling along magnetic field lines produce cyclotron radiation. Magnetic reconnection events where stellar and planetary field lines interact can accelerate particles and produce radio bursts. For close orbiting planets around active stars, these emissions can be detectable from Earth with sensitive radio telescopes. No radio detections have been reported yet for this system, but dedicated monitoring campaigns are planned. The migration pathway. Planetary migration theory has evolved significantly since the first hot Jupiters were discovered in the 1990 seconds. Multiple migration mechanisms have been identified, each operating under different conditions and producing different outcomes. Understanding which mechanism or combination of mechanisms place the impossible planet in its current orbit is crucial for explaining its survival and determining whether similar planets might exist elsewhere. Type 1 migration occurs while a planet is still embedded in the gas disk and is relatively low mass, not yet massive enough to clear a gap in the disk. The planet's gravity creates spiral density waves in the surrounding gas, similar to how a boat creates wakes in water. These waves carry angular momentum away from the planet, causing it to lose orbital energy and spiral inward toward the star. Type I migration can be surprisingly rapid for planets in the Neptune to Saturn mass range, potentially moving a planet from 5 AU to 0.05 AU in just 100,000 years. However, this timescale poses problems. If migration is too fast, planets spiral into their stars before the disk dissipates, eliminating themselves before reaching observable orbits. Type 2 migration occurs when a planet becomes massive enough, typically above Saturn's mass, to open a gap in the protoplanetary disk. The planet's gravity clears out gas from its immediate orbital vicinity, creating a region of lower density. The planet then becomes locked to the disk's viscous evolution, migrating inward at the rate the disk itself accretes onto the star. Type 2 migration is generally slower than Type 1, proceeding over timescales of millions of years. This slower pace might allow migration to halt when the disk dissipates, leaving the planet in a stable, close orbit rather than plunging it into the star. For the newly discovered planet, Type 2 migration seems most applicable given its Jupiter-like mass. Simulations of Jupiter mass planets embedded in protoplanetary disks around red dwarfs show that these planets can indeed migrate inward and reach very close orbits. The key parameter is disk lifetime, how long the gas disk survives before photoevaporation from the star or dispersal by stellar winds removes it. Observations of red dwarf systems suggest disk lifetimes range from 1 to 10 million years, with significant variation between systems. If the disk survived long enough, Type 2 migration could transport the planet from its formation location beyond 5 AU to the inner system. However, stopping the migration at precisely 0.03 AU requires a special mechanism. The most commonly invoked process is tidal interaction with the star. As the planet migrates very close to the star, tidal forces become significant. These forces transfer angular momentum from the star's rotation to the planet's orbit, potentially halting inward migration and even causing outward migration if the star rotates sufficiently rapidly. The balance between disk-driven inward migration and tide-driven outward migration could establish an equilibrium orbital distance. Once the disk dissipates, the planet remains at this distance, stabilized by tidal forces alone. An alternative migration mechanism involves gravitational interactions with other planets. In multi-planet systems, planets can exchange angular momentum and energy through their mutual gravitational perturbations. These interactions can pump up orbital eccentricities, causing planet orbits to become elongated. If a planet's orbit becomes sufficiently eccentric, it can pass very close to the star at perihelion, the closest approach point. Tidal forces during these close passages dissipate orbital energy, gradually circularizing the orbit at a small semi-major axis. This mechanism, called high eccentricity migration or Kozai-Leadoff migration when involving a third body, can place planets in extremely close orbits without requiring them to travel smoothly through the disk. The observed small but non-zero orbital eccentricity of 0.02 to 0.04 provides a hint about migration history. Pure Type II disk migration tends to circularize orbits efficiently, leaving planets with nearly zero eccentricity. The maintained eccentricity might indicate that high eccentricity migration played a role, or that the planet experienced dynamical interactions that excited eccentricity after disk dispersal. Alternatively, the eccentricity might be actively maintained by interactions with an as-yet undetected companion planet in the system, a possibility that motivates searches for additional planets through both radial velocity monitoring, transit searches. Computer simulations exploring these scenarios reveal a sobering truth. Successfully delivering a gas giant to 0.03 AU around a red dwarf without it either falling into the star or retaining a highly eccentric orbit requires a narrow range of initial conditions and disk properties. The parameter space that yields stable, close-orbiting gas giants is small. Perhaps only a few % of simulated systems produce such outcomes. This suggests that the impossible planet might be genuinely rare, requiring a fortuitous combination of circumstances to exist. Yet its existence proves the process is possible, implying there should be other examples awaiting discovery. The role of disk composition. The composition and mass of the protoplanetary disk play critical roles in determining what kinds of planets can form and whether gas giants can reach ultra-close orbits. Red dwarf protoplanetary disks differ significantly from disks around Sun-like stars in several important ways. They contain less total mass, are smaller in extent, and have different temperature structures. These differences affect every stage of planet formation and migration. Observations of young red dwarf systems using telescopes like ALMA have revealed that their protoplanetary disks typically contain between 10 and 100 Earth masses of material, roughly 10 times less massive than disks around solar-type stars. This lower mass presents an immediate problem for gas giant formation. Building a Jupiter-mass planet requires gathering material from a large region of the disk. If the total available mass is limited, either the planet cannot form at all, or it must form through extraordinarily efficient accretion processes that concentrate most of the disk's mass into a single planet. The disk's radial extent also matters. Observations show that red dwarf disks extend to smaller maximum radii than disks around more massive stars, typically 30 to 100 AU compared to 100 to 500 AU for solar-type stars. A smaller disk means less total solid material in the outer regions where gas giant cores form. It also affects migration. A planet forming in a smaller disk has less distance to migrate to reach the inner system. From a formation perspective, the smaller disk makes gas giant formation more difficult. From a migration perspective, it might actually facilitate reaching ultra-close orbits because there's simply less distance to cover. The disk's lifetime critically affects whether migration can deliver planets to close orbits before the disk disperses. High-energy radiation from the star, particularly far ultraviolet light, heats the disk's surface, driving photoevaporative winds that remove gas. For red dwarfs, this process is complex. While these stars emit less total ultraviolet radiation than Sun-like stars, they're often more active with frequent flares, and their disks are lower mass and potentially easier to disperse. Observations suggest red dwarf disk lifetimes average around 3 to 5 million years shorter than the 5 to 10 million years typical around solar-type stars. The shorter disk lifetime creates a timing problem. If a gas giant forms beyond the snow line and begins migrating inward through Type 2 migration, it might not have sufficient time to reach ultra-close orbits before the disk disappears and migration halts. Calculations show that migrating from 5 AU to 0.03 AU requires several million years under typical disk viscosity conditions. This is uncomfortably close to the disk lifetime, suggesting that only in systems where the disk survives longer than average, perhaps due to lower stellar activity or higher initial disk mass, can migration proceed far enough to deliver planets to extreme orbits. However, disk composition might provide a loophole. If the disk is unusually metal-rich, enriched in elements heavier than hydrogen, and helium planet formation can proceed more efficiently. Heavy elements form the solid materials that build planetary cores, so a higher metallicity disk contains more planet-building material for a given total disk mass. Observations have established a correlation between stellar metallicity and gas giant occurrence. Stars with higher metallicity are more likely to host gas giants. If the impossible planet's host star has above-average metallicity for a red dwarf, this might explain how a Jupiter-mass planet formed despite the disk's limited total mass. Webb's stellar spectroscopy provides some information about the star's composition. Analysis of absorption lines in the stellar spectrum yields metallicity measurements. Preliminary results suggest the star has a metallicity close to solar, significantly higher than typical for red dwarfs, which tend to be metal poor on average. This elevated metallicity might be the key factor that enabled gas giant formation in this system. With more heavy elements available, the planet's core could grow faster and larger, reaching the critical mass for gas capture sooner and forming a full gas giant despite the disk's modest total mass. The disk's turbulent properties also influence migration rates and outcomes. Turbulence in the gas disk, likely driven by the magnetorotational instability, determines how efficiently angular momentum is transported and how viscous the disk behaves. Higher turbulence generally means faster migration, but also more stochastic, random variations in migration rates. Low turbulence produces slower, more predictable migration. The level of turbulence in red dwarf disks remains uncertain. Different theoretical models and observational constraints yield conflicting predictions. If these disks are less turbulent than disks around Sun-like stars, migration might proceed more slowly, giving more time for the disk to evolve and potentially allowing planets to survive that would otherwise spiral into their stars. Alternative formation scenarios. While migration from the outer disk remains the leading explanation for the impossible planet, astronomers have explored alternative formation scenarios that might explain ultra-close gas giants. These alternatives challenge conventional wisdom about where and how gas giants can form, invoking conditions and processes that push the boundaries of planetary formation theory. One intriguing possibility is in situ formation, the idea that the gas giant formed directly at its current orbital distance, rather than migrating from afar. Standard theory says this shouldn't work. The inner disk is too hot for volatile ices to condense, providing insufficient, solid material to build the massive cores needed for gas capture. However, some theorists have proposed that under specific conditions, massive cores might form close to the star through alternative pathways. The pebble accretion mechanism offers one possible route. In this model, small dust particles grow into pebble-sized objects, centimeters to meters across, through gentle collisions. These pebbles then experience strong aerodynamic drag from the surrounding gas, causing them to spiral inward toward the star. A planetary embryo, even a relatively small one, of just a few Earth masses, can gravitationally focus and capture these inflowing pebbles extremely efficiently. The embryo can grow to 10 or more Earth masses rapidly, potentially reaching the critical mass for gas capture even in the inner disk where conditions are otherwise unfavorable. For this mechanism to work in the inner disk, several requirements must be met. First, there must be a steady supply of pebbles drifting inward from the outer disk. Second, the embryo must form early, before too much material has accreted onto the star or been dispersed. Third, gas must remain in the inner disk long enough for the growing core to capture a massive envelope. Simulations exploring this scenario show it's theoretically possible, but requires fine-tuning of multiple parameters. The resulting planets tend to have higher core masses relative to their envelopes compared to planets formed in the outer disk, because the core forms by solid accretion rather than capturing large amounts of distant solids embedded in accreted gas. Another alternative invokes gravitational instability in the disk. In very massive, cold disks, gravity can overwhelm pressure support, causing regions of the disk to collapse directly into bound clumps. These clumps contract under their own gravity, potentially forming gas giant mass objects directly from the disk without first building a solid core. This mechanism is thought to be more relevant in the outer regions of massive disks around Sun-like or more massive stars, where conditions favour instability. However, some theorists have speculated that unusual disk conditions, perhaps a massive, rapidly cooling disk, might trigger gravitational instability even in the inner regions around a red dwarf. This scenario faces significant challenges. The inner disk around a red dwarf receives intense stellar radiation, keeping it hot and preventing the cooling necessary for gravitational instability. The disk would need to be extraordinarily massive, possibly containing as much mass as the star itself, to become gravitationally unstable in the inner regions. Such massive disks are not observed around red dwarfs in protoplanetary surveys. Moreover, objects formed by disk instability tend to have compositions similar to the surrounding gas, lacking the heavy element enrichment seen in the impossible planet's atmosphere. This compositional evidence argues strongly against formation through gravitational instability. A third alternative involves planetary embryo scattering and capture. In this scenario, multiple giant planets form in the outer disk. Gravitational interactions between them lead to orbital instabilities. Planets' orbits cross and close encounters occur. These encounters can eject planets from the system entirely or scatter them onto highly eccentric orbits. A planet on an eccentric orbit that brings it very close to the star experiences strong tidal forces during perihelion passage. These tides dissipate orbital energy, gradually circularizing the orbit at a small radius. Over many orbits, the planet spirals down to a close, circular orbit. This mechanism, called tidal circularization, can explain both ultra-close orbits and maintained eccentricity. If circularization is still ongoing, the orbit would retain non-zero eccentricity as observed. The planet's formation in the outer disk is consistent with its atmospheric composition, showing heavy element enrichment. However, this scenario requires the presence of other massive planets to initiate the scattering event planets that would presumably still exist somewhere in the system unless they were ejected. Searches for additional planets through radial velocity monitoring are ongoing and will test this hypothesis. Each alternative scenario makes testable predictions about the planet's properties and system architecture. In situ formation predicts higher core to envelope mass ratios and potentially different atmospheric compositions. Gravitational instability predicts near stellar atmospheric composition with minimal heavy element enrichment. Scattering scenarios predict the presence of additional planets or evidence of past planetary ejections. As observations continue and models improve, astronomers will test these alternatives against the growing body of data, gradually narrowing the range of possible formation histories, rethinking planetary system architecture. The discovery of the impossible planet forces a fundamental rethinking of how planetary systems are organized and what architectures are possible. For decades, our understanding of system architecture was shaped primarily by our own solar system. Small rocky planets orbit close to the Sun, gas giants orbit farther out, and this arrangement seemed natural, almost inevitable. The discovery of exoplanets shattered this view, revealing that planetary systems come in wild varieties of configurations. Hot Jupiter's gas giants orbiting within 0.1 AU of their stars were among the first exoplanets detected in the 1,990 seconds. Their existence challenged formation theories, leading to the development of migration models. But hot Jupiters around Sun-like stars, while surprising, fit within extended models of disk migration and planet-star interactions. The impossible planet takes this a step further. A Jupiter-mass world at only 0.03 AU around a red dwarf represents an even more extreme architecture, one that tests the absolute limits of what migration theories can explain. Statistical studies of exoplanet populations reveal patterns that inform our understanding of system architectures. Gas giants are less common around red dwarfs than around Sun-like stars, a correlation with stellar mass that makes sense given the lower disk masses around smaller stars. When gas giants are found around red dwarfs, they typically orbit at distances greater than 1 AU, well beyond the locations where they formed. Hot Jupiters around red dwarfs are extremely rare in planet surveys, occurring around less than 1% of such stars compared to 1 to 2% around Sun-like stars. This statistical rarity makes the impossible planet even more remarkable. It exists in a regime that both formation theory and observations suggest should be nearly empty. If such planets are genuinely rare, requiring specific and uncommon disk conditions, migration histories, or dynamical events, then this discovery might represent a chance glimpse of an extraordinarily unusual system. Alternatively, detection biases might explain the apparent rarity. Ultra-close planets are actually among the easiest to detect through both radial velocity and transit methods, so observational bias isn't hiding a large population. The rarity appears to be genuine. The presence of an ultra-close gas giant affects the potential for other planets in the system. Massive planets exert strong gravitational influence on their surroundings, shepherding smaller bodies and clearing gaps. For the impossible planet, its close orbit and substantial mass mean its gravitational reach extends outward, potentially destabilizing orbits of smaller planets at distances of a few tenths of an AU. Simulations suggest that additional planets, if present, likely orbit either very close to the gas giant within 0.01 AU in tight resonance, or significantly farther out beyond 0.5 AU where the gas giant's perturbations weaken. This gravitational architecture has implications for habitability. Red dwarfs are of intense interest in the search for habitable worlds because their longevity, they can shine for trillions of years, and abundance make them prime targets. However, a massive close-orbiting planet, like the Impossible Planet, would render much of the inner system uninhabitable through gravitational disruption. The habitable zone around this particular red dwarf, the region where liquid water could exist on a rocky planet's surface, lies at approximately 0.1 to 0.3 AU. Any rocky planets trying to form or maintain stable orbits in this zone would be strongly perturbed by the gas giant at 0.03 AU. The system's architecture also affects the long-term evolution of orbits. Even after the protoplanetary disk disperses, planets continue to interact gravitationally. In systems with multiple planets, these interactions can excite eccentricities and inclinations over millions to billions of years, potentially leading to orbital instabilities and planet-planet collisions or ejections. The Impossible Planet's orbit, while currently stable, might evolve over time. Tidal interactions with the star will continue to modify the orbit, possibly causing very slow inward or outward migration, depending on the star's rotation rate and the strength of tidal dissipation. Long-term stability calculations for single-planet systems around red dwarfs generally show good stability over billions of years. The planet at 0.03 AU is well within the tidal circularization radius, meaning tidal forces have likely already circularized its orbit from any initial eccentricity. The small remaining eccentricity might be maintained by an undetected outer companion, or it might be gradually damping towards zero. Monitoring the system over years to decades will reveal whether the orbit is evolving measurably or remains static. Implications for exoplanet statistics. Every new exoplanet discovery refines our statistical understanding of how common different types of planets are and under what conditions they form. The Impossible Planet, despite being a single object, has significant implications for exoplanet demographics and formation theory. Its mere existence proves that certain planetary configurations previously thought impossible or extraordinarily rare can occur, requiring revision of occurrence rate estimates and formation models. Before this discovery, models of planet formation around red dwarfs predicted that Jupiter-mass planets should be uncommon but not impossible. These models estimated that around 5 to 10% of red dwarfs might host gas giants, primarily at orbital distances beyond 1 AU, where formation conditions are more favourable. Ultra-close gas giants, those orbiting within 0.1 AU, were predicted to be exceedingly rare, perhaps occurring around less than 0.1% of red dwarfs. The discovery of the Impossible Planet at 0.03 AU suggests that either the actual occurrence rate is somewhat higher than predicted, or this system represents an exceptionally rare case that we happen to find through fortunate timing. The discovery's timing is relevant because the planet was found through a survey targeting young stellar systems. Most exoplanet surveys focus on mature stars that have finished forming their planets billions of years ago. Young systems, still in the midst of or just completing planet formation, are less commonly studied because they're rarer and more challenging to observe. Their stars are often more variable and active, and their planets might still be accreting material or migrating. Finding such an extreme planet around a young star raises questions about whether ultra-close gas giants are more common in young systems than mature ones, possibly because some are destroyed or migrate into their stars over time. This possibility has important implications for planet survival rates. If ultra-close gas giants form more frequently than we observe them in mature systems, some must be destroyed over time. Mechanisms for destruction include tidal decay, where tidal friction gradually shrinks the orbit until the planet enters the star's atmosphere and is consumed, and atmospheric stripping that reduces gas giants to small rocky cores. The impossible planet's survival for 200 million years suggests it will likely survive much longer, perhaps for the star's entire lifetime. But other planets, in similar orbits, might not be so fortunate if they lack the right combination of mass, composition, and magnetic field strength. The planet's discovery also informs our understanding of migration timescales and mechanisms. If ultra-close gas giants reach their final orbits primarily through disk migration, their occurrence rate should correlate with disk properties, lifetime, mass, viscosity, that determine migration efficiency. If instead they reach close orbits through dynamical scattering and tidal circularization, the occurrence rate should correlate with the frequency of multi-planet systems experiencing instabilities. By studying many systems and looking for correlations between planetary architecture and stellar or disk properties, astronomers can test these competing hypotheses. For theoretical models, the impossible planet provides a crucial benchmark. Models must be able to reproduce not just the planet's final orbit, but also its mass, composition, and survival over 200 million years. This combination of constraints is stringent. Many models might explain one or two features, but fail to explain all of them simultaneously. The planet serves as a test case that can validate or rule out different theoretical frameworks, guiding researchers toward models that capture the full complexity of planet formation and evolution. The discovery also motivates expanded searches for similar planets. If one ultra-close gas giant around a red dwarf exists, there should be others awaiting discovery. Dedicated surveys targeting young red dwarf systems with intensive monitoring might reveal additional examples. These discoveries would establish whether the impossible planet is truly exceptional or merely the first detected member of a previously unknown population. The next generation of telescopes, including ground-based extremely large telescopes and future space missions, will have the sensitivity to detect even smaller and more distant planets, potentially revealing how common these extreme architectures truly are. The broader search for impossible worlds. The impossible planet represents just one example of how exoplanet discoveries continue to surprise and challenge our understanding. Across the thousands of known exoplanets, numerous systems defy expectations or exhibit properties that stretch theoretical models to their limits. These discoveries collectively demonstrate that planet formation and evolution are more diverse and complex than early theories assumed, operating under a wider range of conditions and producing more varied outcomes than our solar system alone would suggest. Consider ultra-short period planets, worlds that orbit their stars in less than one day. These planets, including several with orbital periods under 10 hours, occupy an extreme niche. They orbit so close to their stars that they experience extreme tidal forces, surface temperatures exceeding 2000 degrees Celsius, and stellar radiation intense enough to vaporize rock. Many are likely dissolving, losing mass through evaporation visible as comet-like tails of escaping gas. Their existence raises questions about how they reached such orbits and how long they can survive. Or consider puffy planets, gas giants with anomalously large radii, sometimes approaching twice Jupiter's radius despite having similar mass. These inflated worlds have densities comparable to styrofoam, so low that they would float in a bathtub if such a large bathtub existed. The mechanism inflating their atmospheres remains debated. Is it tidal heating, deposition of stellar radiation deep in the atmosphere, or some other energy source? Each new discovery of an inflated giant provides additional data to test these hypotheses. Then there are circumbinary planets' worlds orbiting binary star systems, experiencing the gravitational pull of two suns, like the fictional planet Tatooine from Star Wars. These planets face unique challenges during formation. The binary star's gravity clears a gap in the protoplanetary disk, and the region of gravitational stability where planets can survive long-term is limited. Yet several circumbinary planets are now known, proving that planet formation can proceed even in these complex environments. Free-floating planets, worlds wandering through interstellar space without host stars, represent another class of impossible objects. Early formation theories didn't predict their existence, yet observations have revealed populations of Jupiter-mass objects drifting alone through young star clusters. These worlds might have formed like stars through direct collapse of gas clouds, or they might be planets ejected from their original solar systems through gravitational interactions. Their existence demonstrates that planetary objects can exist independently of stars, blurring the distinction between planets and brown dwarfs. Each category of extreme exoplanet teaches different lessons about planetary processes. Ultra-hot Jupiters teach us about atmospheric chemistry under extreme temperatures, where metals vaporize and atmospheric winds reach hypersonic speeds. Super-Earths and mini-Neptunes planet types, absent from our solar system but common elsewhere, teach us about planetary interiors, differentiation, and envelope retention in an intermediate mass regime. Eccentric giants teach us about dynamical evolution and planet-planet interactions. The tapestry of exoplanet diversity reflects the full richness of planet formation physics, operating across millions of different initial conditions. The impossible planet contributes to this tapestry by occupying a particularly extreme niche, the closest orbiting gas giant yet found around a red dwarf, in an environment where both formation and survival seem impossible based on first principles. As observations continue and theoretical models improve, this planet will likely transition from impossible to merely extreme, its existence explained within an expanded framework of planetary science that accounts for rare but physically allowed formation pathways and survival mechanisms. This progression mirrors the historical trajectory of scientific understanding. Many phenomena, initially labelled impossible, from meteorites to continental drift to black holes, were eventually accepted and explained as observations accumulated and theories expanded. The impossible planet will likely follow this path, moving from puzzling outlier to understood extreme case. But the lessons it teaches along the way about planetary migration, atmospheric retention, stellar activity, and system architecture will permanently enrich our understanding of how planets form and evolve throughout the galaxy. Future observations and remaining questions. While the James Webb Space Telescope has provided unprecedented detail about the impossible planet, many questions remain unanswered. Future observations using both Webb and other facilities will continue to probe this system, searching for answers to fundamental questions about the planet's nature, history, and prospects for long-term survival. One critical avenue for future study involves monitoring atmospheric composition over time. If the planet is losing its atmosphere at rates significant on observational timescales, hundreds or thousands of years, repeated spectroscopic observations might detect changes in atmospheric abundances or upper atmosphere structure. Comparing spectra taken years or decades apart, could reveal whether light elements like hydrogen and helium are depleting faster than heavier elements, or whether the atmospheric composition remains stable. Current observations provide a snapshot. Time series data will reveal whether that snapshot captures an equilibrium state or an evolving system. Detecting the planet's magnetic field directly remains a priority. While magnetic fields are difficult to measure for exoplanets, several approaches might work. Radio observations using facilities like the Square Kilometre Array might detect auroral emissions generated when stellar wind particles interact with the planet's magnetosphere. These emissions, similar to Jupiter's radio aurora, would confirm the presence of a strong magnetic field and provide constraints on its strength. Alternatively, observations during stellar flares might reveal how the planet's magnetosphere responds to enhanced stellar wind pressure, with compression or disruption signatures visible in the atmospheric spectrum. Searching for additional planets in the system is crucial for understanding its architecture and dynamical history. The small but non-zero orbital eccentricity hints at possible gravitational perturbations from another planet. Radial velocity monitoring with high-precision spectrographs can detect the gravitational tugs of additional planets, potentially revealing whether the system hosts other worlds. Transit searches with long-duration photometric monitoring might catch additional planets crossing the star's face, though geometric probabilities make this less likely for planets farther from the star. Understanding the star's rotation state and magnetic field will help model star-planet interactions. Stellar rotation affects tidal interactions that can modify planetary orbits over time. The star's magnetic field structure determines how stellar wind and magnetic energy couple to the planet. Measuring stellar rotation through rotational broadening of spectral lines or through star-spot modulation of brightness provides crucial input for tidal evolution models. Mapping the stellar magnetic field structure through Zeeman Doppler imaging, or polarimetry, constrains models of the stellar wind and its interaction with planetary magnetospheres. Long-term photometric monitoring to detect stellar flares will characterize the radiation environment more completely. Webb's observations captured a few flares during limited observing windows, but statistical characterization of flare frequency and energy distribution requires monitoring over months to years. Ground-based telescopes can provide this monitoring at lower cost than space-based observations. Flare statistics inform models of atmospheric escape and chemical evolution, helping determine whether the current atmospheric state can persist over billions of years. High-resolution spectroscopy of the planet's atmosphere during transit and eclipse can probe atmospheric structure with increasing depth. Future Webb observations at different wavelengths and higher spectral resolution might detect additional molecular species not seen in initial spectra. Measurements during secondary eclipse, when the planet passes behind the star, can isolate the planet's thermal emission, providing direct temperature measurements and probing deeper atmospheric layers. These observations will reveal atmospheric temperature-pressure profiles, chemical gradients, and circulation patterns with unprecedented clarity. Comparative studies of similar systems will place the impossible planet in context. As surveys discover additional ultra-close planets around red dwarfs, patterns might emerge that reveal which systems host such planets and why do they preferentially occur around metal-rich stars, around younger or older stars, in systems with particular disk properties or stellar activity levels. Building statistical samples will transform a single puzzling object into a data point within a broader distribution, enabling population-level conclusions about formation and survival mechanisms. Theoretical work will continue refining models of planet formation, migration, and atmospheric evolution. New simulations incorporating improved physics, better treatments of disk turbulence, magnetic fields, photoevaporation, and tidal dissipation will test whether existing frameworks can reproduce the impossible planet's properties or whether fundamentally new processes must be invoked. Matching a single system requires tuning models. Matching a population of systems constrains underlying physics more strongly. The broader lesson from the impossible planet extends beyond this particular system. It demonstrates that our current understanding of planetary systems, while powerful and generally successful, remains incomplete. Nature produces outcomes that our best models struggle to explain, reminding us that the universe is under no obligation to conform to our theories. Every impossible planet discovered forces us to expand our thinking, question our assumptions, and develop more sophisticated frameworks. This iterative process observation challenging theory adapting to accommodate new data, refined theory making testable predictions drives scientific progress. What this means for planetary science. The discovery of the impossible planet marks a significant moment in the development of planetary science as a discipline. For centuries, planetary science studied only one planetary system, our own. Theories were built on a sample size of 8 planets, or 9, depending on definitions and timing, orbiting a single Sunday. The exoplanet revolution expanded that sample to thousands, revealing a cosmos rich in planetary diversity that our solar system alone couldn't represent. Each surprising discovery broadens our understanding of what planetary systems can be. The impossible planet contributes several key insights to this expanding knowledge base. First, it demonstrates that gas giant formation and survival are possible under more extreme conditions than models predicted. This expands the parameter space where we might find gas giants, potentially including regimes previously dismissed as implausible. If Jupiter-mass planets can exist at 0.03 AU around red dwarfs, what other supposedly impossible configurations might await discovery? The answer will come from continued surveys and open-minded interpretation of results. Second, the planet highlights the importance of atmospheric retention mechanisms beyond simple thermal escape calculations. Standard models focusing on Jeans escape thermal evaporation of atmospheric particles clearly miss important physics in extreme environments. Magnetic shielding, ionospheric absorption, and possibly other mechanisms not yet identified must play significant roles in determining atmospheric survival. Future atmospheric evolution models will need to incorporate these effects more comprehensively, moving beyond simplified one-dimensional treatments to three-dimensional simulations that capture the full complexity of star-planet interactions. Third, the discovery underscores the diversity of migration pathways and outcomes. Migration theory successfully explained hot Jupiters around Sun-like stars, but extending those models to red dwarf systems and extreme orbital distances requires careful attention to stellar mass, disk properties, and dynamical evolution. The impossible planet serves as an existence proof that migration can deliver planets to ultra-close orbits around low-mass stars, validating certain theoretical predictions while challenging others. This validation is important because migration remains one of the most uncertain aspects of planet formation theory. Fourth, the planet demonstrates the power of infrared spectroscopy for characterizing exoplanet atmospheres. Webb's ability to detect and analyze molecular abundances in the atmosphere of a distant world represents a technological achievement that enables entirely new categories of scientific investigation. Before Webb, characterizing the atmospheric composition of planets around faint red dwarfs was extremely challenging. Now, detailed chemical inventories are possible, providing formation and evolution diagnostics that were previously inaccessible. This capability will transform exoplanet science over the coming decades as Webb surveys hundreds of planet atmospheres across diverse types and environments. Fifth, the discovery illustrates the value of surveying young stellar systems. Most exoplanet research focuses on mature systems where planets have reached their final configurations. Observing planets during or shortly after formation provides unique insights into formation processes, initial compositions, and early evolution that can't be gleaned from ancient systems. The impossible planet's youth, only 200 million years old, means it retains information about recent formation and migration that might be erased or obscured in billion-year-old systems. Looking beyond this individual system, the impossible planet contributes to ongoing debates about planetary habitability and the prospects for life elsewhere in the universe. Red dwarfs are the most common stars in the galaxy, and their extreme longevity makes them compelling targets for habitability studies. However, the presence of ultra-close gas giants complicates the habitability picture. Such planets might clear out inner rocky planets, enhance stellar activity through tidal interactions, or otherwise render these systems less hospitable for life. Understanding how common these disruptive giant planets are around red dwarfs informs statistical estimates of habitable zone planet occurrence rates. At the same time, the planet's survival against all odds inspires a kind of cosmic optimism. If planets can persist in environments this extreme, bathed in intense radiation, stripped by powerful stellar winds, locked in gravitational embraces with their stars, then perhaps life too can find footholds in surprising places. This doesn't mean the impossible planet itself is habitable. It almost certainly isn't. But if one impossible thing can exist, others might too. The universe appears more permissive of extreme phenomena than our theories sometimes suggest. The nature of scientific discovery. The story of the impossible planet illuminates how scientific discovery actually works, not as a steady accumulation of facts, but as a dialogue between observation and theory, punctuated by surprises that force conceptual revolutions. Every major discovery in exoplanet science has followed this pattern. Surprising observation, initial skepticism, attempted explanations within existing frameworks, eventual recognition that frameworks need expansion, development of new theories, and finally integration of the anomaly into an enlarged understanding. When the first hot Jupiter, 51 Pegasi b, was discovered in 1995, the initial reaction was disbelief. Several teams suspected instrumental errors or misinterpretation of data. Gas giants orbiting that close to stars violated everything astronomers thought they knew about planetary system architecture. Only after multiple independent confirmations did the community accept that hot Jupiters were real, triggering the development of migration theory to explain them. A generation later, migration theory is taught in textbooks, and hot Jupiters are understood as a natural, if somewhat uncommon, outcome of planet formation processes. The impossible planet follows a similar trajectory, though its journey from anomaly to understood phenomenon is still ongoing. The initial observation prompted questions about data quality and interpretation. Were the spectroscopic signatures correctly identified? Could this be some other type of object masquerading as a close-orbiting gas giant? As confirming evidence accumulated, attention shifted to physical explanations. How did it form? How does it survive? What processes maintain its stability? Scientists are currently in this phase, proposing and testing mechanisms that might explain the planet's existence. This process reveals science's self-correcting nature. Theories are not sacred. They're tools for organizing knowledge and making predictions. When observations contradict predictions, scientists don't discard the observations, they question the theories. Sometimes minor adjustments suffice, tweaking parameters, incorporating previously neglected effects, or refining calculations. Other times, fundamental reconceptualization is required, new physical mechanisms, different formation pathways, or expanded ranges of possible outcomes. The impossible planet likely requires something between these extremes, substantial theoretical development, but not a complete overhaul of planetary formation physics. The discovery also highlights the importance of observational capabilities in driving scientific progress. The impossible planet couldn't have been detected or characterized without Webb's unprecedented infrared sensitivity and spectroscopic capabilities. Many discoveries in science follow technological advances. Microscopes revealed cells. Telescopes revealed galaxies. Particle accelerators revealed quarks. Each new tool opens a window on previously inaccessible phenomena. Webb's deployment has opened new windows on exoplanet atmospheres, star formation, distant galaxies, and more. The impossible planet is one early result. Many more surprises likely await, in data yet to be analyzed, or observations yet to be made. The interdisciplinary nature of understanding this planet deserves emphasis. Explaining its existence requires contributions from multiple scientific fields. Astrophysics provides stellar evolution and radiation environment models. Planetary science contributes formation and migration theories. Atmospheric physics explains chemical composition and escape processes. Magnetohydrodynamics models star-planet magnetic interactions. Computational science enables complex simulations. No single discipline holds all the answers. Progress requires synthesis across specialties, with researchers communicating across subdisciplinary boundaries and integrating diverse types of evidence into comprehensive models. This collaborative, iterative process characterizes modern science. Individual researchers make observations, develop theories, perform calculations, but understanding emerges from the collective enterprise of many teams working on related problems, sharing data, debating interpretations, and gradually converging on explanations that satisfy multiple independent lines of evidence. The impossible planet story is still being written by this global community of scientists, each contributing pieces of the puzzle toward an eventual complete picture. Humanity's position within this cosmic story deserves reflection. We live on a planet orbiting a yellow dwarf star, itself just one of hundreds of billions in our galaxy. Our particular planetary architecture, rocky worlds inner, gas giants outer, isn't even typical of planetary systems in general. We're discovering that the universe contains vastly more diversity than our single example could suggest. Planets exist where we thought they couldn't. Life might emerge in environments we'd consider impossible. The universe is grander, stranger, and more varied than we imagined. This realization comes with humility. Our theories, built on limited samples and Earth-based physics, capture aspects of cosmic reality but not its full richness. Every discovery of an impossible planet is a reminder that the universe isn't obligated to follow our expectations. It operates according to physical laws we're still working to fully understand, producing outcomes that surprise and challenge us. This isn't a failure of science, it's a feature. The fact that the universe continues to surprise us means there's more to discover, more to learn, more frontiers to explore. The impossible planet stands as testimony to this ongoing journey of discovery. It's a world that shouldn't exist according to our theories, yet exists nonetheless. Understanding how and why it exists will advance our knowledge of planetary systems, pushing the boundaries of what we know is possible. And when that understanding is achieved, when the impossible planet becomes merely improbable or unusual but explained, scientists will turn their attention to the next impossible discovery waiting somewhere in the cosmos, because in a universe as vast and ancient as ours, impossible things happen all the time. We just need to keep looking, keep questioning, and keep pushing the boundaries of human knowledge outward into the unknown. The photo-evaporation paradox. When stellar radiation strikes a planetary atmosphere, it doesn't simply warm the gas, it tears it apart atom by atom. This process, known as photoevaporation, represents one of the most destructive forces a close orbiting planet can face. For the impossible planet, orbiting at a mere 0.03 astronomical units from its red dwarf star, photoevaporation should have stripped away its hydrogen-helium envelope within the first few million years of its existence. Yet 200 million years later, the planet remains intact, its atmosphere showing no signs of the catastrophic loss that physics predicts. Understanding why requires examining how photoevaporation operates at the molecular level. When high-energy photons from the star strike atmospheric particles, they can impart ionized energy to break molecular bonds and ionize atoms. Hydrogen atoms, being the lightest, are particularly vulnerable. Once ionized and heated to tens of thousands of degrees, these particles can achieve velocities exceeding the planet's escape velocity. The result is a continuous outflow of material from the upper atmosphere into space, a planetary wind that gradually erodes the envelope. The rate of this erosion depends on several factors: the intensity of stellar radiation, the planet's mass and radius, the atmospheric composition, and the presence of any protective mechanisms like magnetic fields. For a Jupiter-mass planet at 0.03 AU from a young red dwarf, calculations consistently predict mass loss rates that should consume the entire gaseous envelope in 10 to 30 million years. The star's extreme ultraviolet and X-ray output, hundreds of times more intense per unit luminosity than our Sun, drives this process with brutal efficiency. Webb's spectroscopic observations reveal that the planet's upper atmosphere is indeed highly ionized, with strong signatures from ions of common metals like iron and magnesium. These observations confirm that photoevaporation is actively occurring. The star's radiation is hitting the atmosphere and stripping away electrons. Yet the lower atmosphere, where the bulk of the planet's mass resides, appears remarkably stable. The hydrogen and helium abundances match theoretical predictions for an intact gas giant, with no evidence of preferential depletion of lighter elements that would signal significant atmospheric loss. One possible explanation involves atmospheric circulation patterns that could partially shield the lower atmosphere from radiation. On a tidally locked planet, powerful winds transport gas from the scorching day side to the cooler night side. If these winds are strong enough, potentially exceeding several kilometers per second, they might create a dynamic barrier that limits how deeply stellar radiation penetrates. The constantly moving atmosphere could present different layers to incoming radiation, spreading the photoevaporation across a larger volume and reducing the effective loss rate from any single region. Another factor might be atmospheric self-shielding through opacity. As the upper atmosphere ionizes and heats, it becomes increasingly opaque to the same wavelengths that cause ionization. This creates a feedback effect. The more the upper atmosphere absorbs radiation, the less penetrates deeper layers. The ionized upper atmosphere essentially sacrifices itself to protect the bulk atmosphere below. However, this mechanism only delays rather than prevents. Atmospheric loss eventually, the protective layer itself erodes away. The planet's mass also plays a crucial role. At 1.2 Jupiter masses, its surface gravity is strong enough to hold onto gas more effectively than smaller planets. Escape velocity scales with the square root of mass divided by radius. For massive planets, this means atmospheric particles need higher temperatures and thus more energy input to escape. The relationship isn't linear. A planet twice as massive doesn't just hold its atmosphere twice as well, but potentially much more effectively due to the deeper gravitational well. Recent theoretical work suggests that photoevaporation might be less efficient than classical models predict under certain conditions. When atmospheric densities are very high, as they would be near a massive planet's surface, photons can't penetrate as deeply before being absorbed. This creates a photon-starved regime where the energy input per unit volume decreases, reducing the heating and thus the escape rate. The impossible planet, with its substantial mass and likely high atmospheric density, might reside in this regime. Magnetic fields could provide additional protection, but their effectiveness against photoevaporation remains debated. While magnetic fields efficiently deflect charged stellar wind particles, photoevaporation involves neutral atoms gaining enough thermal energy to escape a process that magnetic fields can't directly prevent. However, by reducing heating from stellar wind bombardment, magnetic fields might lower the overall temperature of the upper atmosphere, indirectly reducing photoevaporation rates. Comparing the impossible planet to hot Jupiters around Sun-like stars reveals an interesting pattern. Many hot Jupiters show evidence of ongoing atmospheric escape, extended hydrogen atmospheres detected through transit spectroscopy, comet-like tails of escaping gas, and atmospheric composition suggesting preferential loss of lighter elements. Yet these planets also survive, despite predictions of rapid stripping. The survival rate appears higher than early models suggested, implying that either photoevaporation models overestimate loss rates, or protective mechanisms are more effective than previously understood. The composition of the escaping material matters too. If photoevaporation preferentially removes lighter elements, while heavier elements remain gravitationally bound, the bulk atmosphere could maintain much of its mass even while continuously losing material. The observed metal enrichment in the planet's atmosphere 3 to 5 times stellar values might actually help stabilize the envelope. Heavier molecules have lower scale heights and are less susceptible to escape, potentially creating a progressively more stable atmosphere over time as lighter elements preferentially leave. Timescales complicate the picture further. At 200 million years old, the system is still quite young. The star remains highly active, producing intense radiation and frequent flares. Yet the planet has survived this most dangerous period. As the star ages and its activity level decreases, a process that typically occurs over the first billion years, photoevaporation rates will decline. If the planet can weather the early storm, its long-term survival becomes increasingly likely. Chemical fingerprints of formation. Every planet carries within its atmosphere a chemical record of its birth, a fingerprint written in the ratios of elements that reveals where and how it formed. For the impossible planet, Webb's spectrographs decoded this fingerprint with unprecedented clarity, revealing abundances that tell a story stretching back to the planet's first moments in a protoplanetary disk long since vanished. These chemical signatures don't just confirm that the planet formed far from its current location. They provide specific constraints on the temperature and composition of the nebula region where it assembled its mass. The most telling signatures come from the planet's enrichment in heavy elements. Spectroscopic analysis shows carbon to hydrogen and oxygen to hydrogen ratios elevated by factors of 3 to 5 compared to the host star. This enrichment isn't uniform across all elements. It follows a specific pattern that points to solid accretion during formation. When planets grow by accumulating solid particles coated with ices, they incorporate more heavy elements per unit mass than if they simply captured gas from the surrounding nebula. The observed enrichment pattern matches predictions for core accretion beyond the snowline, where water ice becomes stable. Water vapor detection adds another layer to this story. The amount of water in a giant planet's atmosphere depends critically on where in the disk it formed. Just beyond the snowline, water ice becomes available, but in limited quantities since temperatures are still relatively warm. Farther out, where temperatures drop below 50 Kelvin, not only water, but also carbon monoxide, methane, and ammonia can condense as ices. The impossible planet's water abundance measured through absorption features in Webb's transit spectra exceeds what simple models predict for formation just beyond the snowline. This suggests the planet formed much farther out, possibly 10 to 20 astronomical units from the star, where multiple volatile species could contribute to its composition. Carbon monoxide deserves special attention. This molecule, detected clearly in the planet's spectrum, provides a sensitive thermometer for formation conditions. Carbon monoxide ice becomes stable only below about 28 Kelvin temperatures, found exclusively in the cold outer regions of protoplanetary disks. Its presence in significant quantities indicates that either solid CO ice accreted onto the growing planet, or gas phase CO from the outer disk mixed into the planet-forming region during its growth. Either scenario requires formation far beyond the snow line, in regions where the young red dwarf's feeble luminosity kept temperatures extremely low. The carbon-to-oxygen ratio offers another diagnostic tool. This ratio varies throughout protoplanetary disks because different carbon and oxygen-bearing molecules condense at different temperatures. Water ice, dominated by oxygen, becomes stable before carbon-rich species like methane and carbon monoxide. A planet forming just beyond the water snowline preferentially accretes oxygen-rich ices, producing a low carbon-to-oxygen ratio. One forming farther out, where carbon-rich ices also condense, achieves higher carbon-to-oxygen ratios. The impossible planet's measured ratio falls in the middle range, consistent with formation at intermediate to large distances where both water and carbon-bearing ices contributed to its growth. Methane adds complexity to the interpretation. This molecule forms through chemical reactions in the disk and becomes increasingly abundant in colder regions. Its detection in the planet's atmosphere, along with the carbon monoxide, creates an apparent puzzle. These molecules typically don't coexist in chemical equilibrium at the high temperatures observed on the planet's day side. The solution likely involves atmospheric dynamics. Methane and carbon monoxide could form on the cooler night side or in deeper, cooler atmospheric layers, then be transported to observable altitudes by powerful winds before photochemical processes destroy them. Isotope ratios, though challenging to measure, provide even more refined constraints on formation conditions. The ratio of deuterium to hydrogen, for example, varies throughout protoplanetary disks and depends on temperature during the disk's early evolution. Similarly, ratios of oxygen, isotopes oxygen 1,6, oxygen 1,7, oxygen 1,8, can indicate whether water came from local ice or was inherited from the molecular cloud that formed the star system. While Webb's current data don't yet resolve these subtle isotopic signatures, future observations with higher spectral resolution might unlock this information. The nitrogen abundance presents another clue. Nitrogen in giant planet atmospheres typically appears as molecular nitrogen, N2. or ammonia, NH3. These species condense at very low temperatures, with ammonia ice forming around 70 Kelvin and nitrogen ice around 35 Kelvin. If the planet formed in regions cold enough for significant nitrogen incorporation, its total nitrogen to hydrogen ratio should exceed stellar values. Preliminary measurements suggest moderate nitrogen enrichment, consistent with formation in cool outer disk regions, but not in the extremely cold zones beyond 30 AU. Metal lines in the transmission spectrum provide additional constraints. Elements like sodium, potassium, iron, and magnesium show characteristic absorption features when present in the upper atmosphere. The relative strengths of these features depend on atmospheric temperature, pressure, and composition. By modeling these line profiles, astronomers can infer not just the presence of metals, but their abundance relative to hydrogen. The observed metal abundances, while elevated compared to the star, remain within ranges expected for core accretion models, suggesting the planet didn't form through direct gravitational collapse, which would produce stellar-like compositions. Comparing the impossible planet to solar system giants provides context. Jupiter shows heavy element enrichment of 2 to 4 times solar values, similar to the impossible planet. Saturn's enrichment is higher, approaching 10 times solar values, while Uranus and Neptune show even more extreme enrichments. These differences reflect where and how each planet formed. Jupiter, forming relatively close to the Sun where solid density was higher, could grow quickly and capture substantial gas before enriching too much. The impossible planet's composition suggests similar formation efficiency, rapid core growth, followed by gas capture before excessive solid accretion. The envelope to core mass ratio offers insights into formation timing. If the planet formed slowly, allowing its core to accrete substantial solid material before capturing gas, the core would be relatively massive, perhaps 20 to 30 Earth masses. If formation occurred rapidly, with gas capture beginning early, the core might contain only 10 to 15 Earth masses. While direct measurement of the core mass remains impossible with current techniques, atmospheric composition provides indirect constraints. The observed heavy element enrichment implies a core mass of approximately 15 to 25 Earth masses, consistent with efficient but not exceptionally rapid formation, the mystery of planetary migration speed. When a gas giant migrates through a protoplanetary disk, the process unfolds according to well-established physical laws governing gravitational interactions between planets and their surrounding gas. These laws predict specific migration timescales, how long a planet should take to travel from its formation location to its final orbit. For the impossible planet, which must have migrated from beyond 10 astronomical units to 0.03 AU, the predicted timescale creates a troubling paradox. The migration should have either happened too quickly, causing the planet to spiral into the star, or too slowly, failing to reach its current position before the gas disk dissipated. Type 2 migration, applicable to massive planets like Jupiter-mass worlds, occurs when the planet opens a gap in the protoplanetary disk. The planet's gravity clears out a region around its orbit, creating a zone of lower density. Once this gap forms, the planet's migration rate becomes tied to the viscous evolution of the disk itself, how quickly gas flows inward toward the star. This process typically operates on timescales of 1 to 10 million years, matching the observed lifetimes of protoplanetary disks around most stars. For red dwarf systems, complications multiply. Red dwarf disks are less massive than those around Sun-like stars, containing perhaps only 30 to 50 Earth masses of material, compared to several hundred around solar-type stars. Lower disk mass affects migration through multiple pathways. Less mass means weaker torques acting on the planet, potentially slowing migration. However, it also means less material to remove from the gap, potentially allowing faster gap opening and earlier onset of Type 2 migration. The balance between these effects determines actual migration rates. Disk viscosity plays a crucial role in controlling migration speed. Viscosity, essentially the stickiness of the gas, determines how quickly angular momentum can be transported through the disk. High viscosity means efficient angular momentum transport and faster inward gas flow, pulling the migrating planet along more rapidly. Low viscosity produces slower, more gradual migration. The source of disk viscosity remains debated. It might arise from turbulence, driven by magnetic fields, magnetorotational instability, or from gravitational instabilities in the disk itself. Different mechanisms produce different viscosity values, leading to uncertainty in predicted migration rates. For the impossible planet to reach 0.03 AU, it needed to migrate roughly 200 AU if it formed at 10 AU, or potentially much farther if it originated at greater distances. Type 2 migration rates vary, but typical values suggest movement of 1 to 5 AU per million years. At these rates, migrating from 10 AU to 0.03 AU requires 2 to 10 million years, cutting it close against disk lifetimes. If the planet formed farther out, the required migration time increases, potentially exceeding available disk lifetime. This timing problem becomes more acute when considering red dwarf disk lifetimes. Observations suggest these disks dissipate relatively quickly, often within 3 to 5 million years. The star's ultraviolet radiation drives photoevaporation, similar to atmospheric photoevaporation but affecting the disk's outer regions. As gas is heated and expelled, the disk loses mass from the outside in, eventually becoming too tenuous to drive further migration. If the disk disperses before the planet completes its inward journey, migration halts, potentially leaving the planet stranded at an intermediate orbital distance. One possible solution involves early, rapid migration, followed by a stall. If the planet formed quickly within the first million years of the disk's lifetime, it could begin migrating while the disk was still massive and capable of driving rapid inward motion. As the disk aged and lost mass through accretion and photoevaporation, migration would slow. If this slowdown occurred at just the right time, the planet could settle at 0.03 AU rather than continuing into the star. This scenario requires fortunate timing but remains physically plausible. Alternative migration mechanisms might explain faster transit times. High eccentricity migration, where gravitational interactions with other planets pump up the orbit's eccentricity, can transport planets to very close orbits without requiring smooth migration through the entire disk. In this scenario, the planet's orbit becomes highly elliptical, bringing it very close to the star at perihelion. Tidal forces during these close passages gradually circularize the orbit, eventually leaving the planet on a close, nearly circular path. This process can be faster than disk-driven migration, potentially completing within 1 to 3 million years. Evidence for high eccentricity migration would include the planet's current, small, but non-zero eccentricity 0.02 to 0.04, which matches expectations for an orbit still undergoing tidal circularization. If the planet arrived via this mechanism, its orbit should slowly become more circular over time as tidal dissipation continues. The process would also require the presence of at least one other massive planet in the system to provide the gravitational perturbations necessary to excite eccentricity. Searches for additional planets through radial velocity monitoring continue, but have not yet yielded confirmed detections. Disk properties might differ from typical assumptions. If the impossible planet's protoplanetary disk was unusually massive, viscous, or long-lived, migration could proceed faster or continue longer than models predict. Some red dwarf disks, particularly those around more massive red dwarfs near the M-dwarf, K-dwarf boundary, can retain gas for up to 10 million years, double the typical lifetime. A longer-lived disk provides more time for migration, potentially allowing the planet to reach its current position even if migration rates were relatively slow. The role of the disk's inner edge adds another consideration. Protoplanetary disks don't extend all the way to the stellar surface. They have inner edges, where gas density drops sharply. This inner edge is often located at the magnetospheric truncation radius, where the star's magnetic field becomes strong enough to prevent gas from accreting further. For red dwarfs, this radius typically sits at 0.02 to 0.05 AU. If the disk's inner edge was located near 0.03 AU, migration would naturally stall there as the planet encounters the disk boundary. Beyond this edge, the density is too low to exert significant torques, halting further inward motion. Planet-disk interactions could create feedback loops affecting migration speed. As the planet migrates inward, it redistributes disk material, potentially changing the disk's density structure and viscosity. These changes modify the torques acting on the planet, which in turn affects its migration rate. In some scenarios, this feedback stabilizes migration at specific orbital distances, creating preferred locations where planets tend to accumulate. Whether 0.03 AU represents such a preferred location around red dwarfs remains an open question requiring more observations of similar systems. The temperature inversion enigma. Temperature inversions regions where atmospheric temperature increases rather than decreases with altitude are common in solar system planets. Earth's stratosphere exhibits an inversion due to ozone absorbing ultraviolet sunlight. Jupiter's stratosphere shows similar behavior. For the impossible planet, Webb's observations revealed an unexpected temperature structure in the upper atmosphere that defies simple heating models. Understanding this temperature profile is crucial because it affects atmospheric chemistry, circulation patterns, and the planet's long-term stability. Standard atmospheric models predict that temperature should decrease with altitude in the upper atmosphere of close-orbiting gas giants. As you move away from the planet's interior heat source and the layers warmed by stellar radiation, temperatures should drop until reaching the upper atmosphere where stellar heating becomes significant again. This creates a temperature minimum layer, followed by warming in the thermosphere where high-energy photons from the star deposit energy. For the impossible planet, observations suggest more complex behavior, possible temperature increases at intermediate altitudes, where simple models predict cooling. The detection of emission features rather than absorption features in certain molecular bands provides evidence for temperature inversions. When atmospheric temperature decreases with altitude, molecules absorb starlight passing through the atmosphere during transit, creating absorption features in the spectrum. When temperature increases with altitude, those same molecules can emit light, creating emission features. Webb's observations show both absorption and emission from different molecular species, suggesting a layered temperature structure with regions of both normal and inverted temperature gradients. What could cause such inversions? Several mechanisms can heat the upper atmosphere beyond simple stellar irradiation. One possibility involves absorption of stellar radiation by high-altitude hazes or clouds. If the atmosphere contains particles that efficiently absorb visible or near-infrared light, perhaps condensates of refractory metals like iron or titanium that vaporize on the hot day side, these particles could heat their surroundings, creating a warm layer aloft. The heat would then radiate downward and upward, producing a temperature inversion. Chemical reactions might also contribute. When stellar ultraviolet radiation breaks apart molecules in the upper atmosphere, the resulting fragments can recombine in exothermic reactions that release heat. For example, atomic hydrogen, produced by photodissociation of molecular hydrogen, can recombine catalytically on dust-grained surfaces, releasing significant energy. Similarly, oxygen atoms from dissociated water molecules can recombine to form molecular oxygen or ozone, both exothermic processes. If these reactions occur at high enough rates, they could heat the upper atmosphere substantially. Tidal heating provides another potential mechanism. While tidal heating primarily affects the planet's interior, the energy released must eventually escape. Some of this energy might be transported to upper atmospheric layers through convection and advection, warming them from below. The planet's small orbital distance and modest eccentricity generate continuous tidal dissipation. If a fraction of this energy channels into the upper atmosphere, it could maintain elevated temperatures at altitudes where stellar heating alone is insufficient. Atmospheric dynamics could redistribute heat vertically in unexpected ways. Powerful winds driven by the day-night temperature contrast might create upwelling regions where hot gas from deeper layers rises into the upper atmosphere. If this upwelling occurs efficiently, it could transport enough heat to maintain warm upper layers. Similarly, breaking gravity waves, atmospheric waves that propagate upward and deposit energy when they break, might heat the upper atmosphere through mechanical dissipation of kinetic energy. The planet's magnetic field might play a role through Joule heating. As the ionized upper atmosphere moves through the planet's magnetic field, electric currents are induced. These currents encounter resistance, dissipating energy as heat through Joule heating, the same process that makes electric stove burners glow. For a planet with a strong magnetic field and a highly ionized atmosphere, Joule heating could contribute significantly to upper atmospheric temperatures, particularly at high latitudes, where magnetic field lines are strongest. Stellar wind interactions could heat the upper atmosphere through shock heating. When the stellar wind, a stream of charged particles flowing outward from the star, encounters the planet's magnetosphere or upper atmosphere, it can form a bow shock similar to the sonic boom created by supersonic aircraft. The compression and heating at this shock front could elevate temperatures in the outermost atmospheric layers. During stellar flares, when the stellar wind intensifies dramatically, this heating could become particularly strong. Understanding the temperature structure is more than academic, it determines the planet's chemical inventory. Chemical reactions proceed at rates that depend exponentially on temperature. A region a few hundred degrees hotter than expected can host entirely different chemistry, with different reaction pathways dominating. For instance, higher temperatures favor dissociation of molecules into atoms and prevent condensation of species that would otherwise form clouds. The observed presence of carbon monoxide and water vapor at high altitudes might indicate these molecules survive because temperatures are lower than the extreme dayside values preserved in thermally inverted cooler layers. The temperature structure also affects atmospheric escape. Photoevaporation proceeds most efficiently when the upper atmosphere is very hot above 10,000 Kelvin and when density is relatively high. If a temperature inversion creates a region of intermediate temperatures around 3,000 to 5,000 Kelvin, this could form a bottleneck that reduces the efficiency of atmospheric escape. Hot lower layers drive expansion, but the cooler inverted layer above acts as a partial barrier, slowing the outflow of gas and reducing loss rates below predictions based on simple temperature profiles. Observing temperature inversions directly requires sophisticated spectroscopic techniques. High-resolution spectroscopy during transit can probe different atmospheric layers by examining absorption features at various wavelengths. During secondary eclipse, when the planet passes behind the star, emission spectroscopy reveals the planet's thermal emission, providing direct temperature measurements. Webb's observations during both transit and eclipse have begun to constrain the temperature profile, though ambiguities remain. Different molecular opacity sources and uncertain cloud properties complicate the interpretation. Resonant interactions and orbital dynamics. When planets orbit stars, their gravitational fields create subtle patterns in the surrounding space patterns that can trap other bodies in resonant relationships or destabilize entire planetary systems. Orbital resonances occur when the orbital periods of two bodies form simple integer ratios, like 2:1 or 3:2, causing their gravitational interactions to reinforce over time. For the impossible planet, its current orbital configuration might result from or be affected by resonances that shaped its migration history and determine its long-term stability. Mean motion resonances represent the most common type of planetary resonance. Two planets are in mean motion resonance when their orbital periods maintain a simple ratio. Jupiter and Saturn nearly achieve a 5:2 resonance, while Neptune and Pluto are locked in a 3:2 resonance that actually protects Pluto from close encounters despite orbital crossing. These resonances can either stabilize or destabilize orbits depending on specific conditions. In migrating systems, planets can be captured into resonances as they move through the disk, potentially affecting where migration halts. For the impossible planet, resonances could have played crucial roles at multiple stages. During migration, if another planet existed in the system, the two could have been captured into resonance, with their migration becoming linked. This resonant migration can protect planets from spiraling into their stars. The inner planet's inward motion pulls the outer planet along, while the outer planet's gravity prevents the inner one from falling too close to the star. The system reaches an equilibrium where both planets migrate together, maintaining a fixed period ratio. Evidence for past or present resonances might appear in the planet's orbital elements. The small but non-zero eccentricity of 0.02 to 0.04 could be maintained by resonant perturbations from an unseen companion. In many resonances, eccentricity is excited as a natural consequence of the gravitational interactions to planets on initially circular orbits develop eccentricity when captured into resonance. If the impossible planet resides in a resonance with another body, its eccentricity might represent a resonant equilibrium rather than a state still evolving through tidal circularization. Secular resonances provide another class of orbital interactions. Unlike mean motion resonances, which involve orbital periods, secular resonances affect the precession of orbital elements, the slow rotation of the orbit's orientation in space. An elliptical orbit's long axis precesses over time, typically completing a cycle in thousands to millions of years. If this precession rate matches the precession rate of another body, secular resonances can occur, pumping up eccentricity or inclination over long timescales. The Kozai-Lidov mechanism represents a special case of secular resonance involving three or more bodies. In this scenario, a distant third body, perhaps a stellar companion or a distant giant planet, can cause periodic oscillations in the inner planet's eccentricity and inclination. The eccentricity can grow very large, bringing the planet extremely close to the star at perihelion. Tidal forces during these close passages then circularize the orbit, eventually leaving the planet on a close, nearly circular orbit. This mechanism has been invoked to explain some hot Jupiters and could potentially explain the impossible planet's location. Evidence for the Kozai-Lidov mechanism would include the presence of a distant companion, and perhaps the planet's small inclination relative to the star's equator. If the planet arrived via high eccentricity migration driven by Kozai-Lidov oscillations, it might orbit at a different angle than planets that formed in the disk and migrated smoothly. Measuring the planet's orbital inclination relative to the stellar equator requires careful observations of stellar rotation and the planet's transit geometry data that could be obtained from future high-precision photometry and spectroscopy. Chaotic zones exist near resonances, where small perturbations can produce large, unpredictable changes in orbital elements. These regions are dynamically unstable over long timescales. Planets that wander into chaotic zones may eventually experience close encounters or collisions. The impossible planet's long-term stability depends on whether it resides in a stable, resonant configuration or merely passed through a resonance during migration. Numerical simulations integrating the orbit forward millions of years can test stability, but require knowing all planets and masses in the system accurately. Three-body resonances involve more complex relationships between three planets or a planet and two additional bodies. These resonances can create extremely stable configurations where three bodies protect each other from close encounters. The Galilean moons of Jupiter Io, Europa, and Ganymede reside in a three-body resonance called the Laplace resonance, where their orbital periods maintain a 4:2:1 ratio. If the impossible planet is part of a multi-planet system, three-body resonances might help explain its position and stability. Tidal evolution interacts with resonances in complex ways. As tides dissipate orbital energy, they cause planets to migrate and their orbits to evolve. This tidal migration can push planets toward or away from resonances depending on the configuration. Sometimes tides break resonances that formed during disk migration as the planet's orbit continues evolving after the disk disperses. Other times, tides can capture planets into resonances that weren't present initially. The interplay between tidal forces and resonant dynamics determines the final orbital architecture. Observational signatures of resonances might appear in long-term monitoring data. If another planet exists in resonance with the impossible planet, transit timing variations would reveal periodic deviations from a strict Keplerian orbit. These deviations, advances, and delays in transit times result from gravitational tugs between the planets. The pattern of timing variations contains information about the companion's mass, orbital period, and the specific resonance involved. Years of continuous monitoring with Webb and ground-based telescopes could detect these subtle signals. Resonances also affect the system's evolution on billion-year timescales. Even stable resonances slowly evolve as tidal forces and stellar mass loss modify orbital periods. The impossible planet's current position might represent a temporary resonance location where the planet will remain for tens or hundreds of millions of years before tidal evolution moves it to a new configuration. Alternatively, the planet might have already evolved out of the resonance that delivered it to its current orbit, now residing in a post-resonance stable state.